Hey friend, it's Dastardly Danny. I picked up your distress signal. I see you drifting into deep space, but you're wide awake. Don't worry, I got you.
Hey guys, this is Dastardly Danny. We're going to go ahead and continue right where we left off, reading the Apollo Operations Handbook Lunar Module Volume 1. We're moving into Section 2, so let's go ahead and read that introduction and get started, shall we? So, introduction, this is the subsystems data to include description of functions and components and failure modes, design data, operational limitations, and telemetry measurements. Subsections 2.2 through 2.1 present data grouped by subsystems as follows: guidance, navigation, and control. Main propulsion, reaction control, electrical power, environmental control, communications, explosive devices, and instrumentation. Subsection 2.10 deals with the miscellaneous subsystems data. Subsection 2.11 presents the detail of crew, personal, equipment. Okay, great. So the subsystems interfaced. Most LM functions are fulfilled by a subsystem or a section of a subsystem, functioning with other subsystems to provide a highly reliable system. The interfacing of the LM subsystem is described in each subsection as applicable. Guidance, Navigation, and Control Subsystem, the introduction. The Guidance, Navigation, and Control Subsystem, the GN and CS, provides vehicle guidance, navigation, and control required for successful completion of a manned LM mission. The subsystem is an aided inertial system whose principal sensors are gyroscopes, accelerometers, an optical device, and radar. The GN and CS consist of the following sections: primary guidance and navigation sections, PGNS, abort guidance section, AGS, and control electronics section, CES. And GN and CS also contains a rendezvous radar, or the RR, a landing radar, LR, and an orbital rate display, Earth and Lunar, or DEAL. Figure 2.2-1 shows the location of the GNNCS equipment. Refer to the paragraph 2.2.4 for a detailed description of the equipment. Primary guidance and navigation section. The PGNS provides the measuring and data processing capabilities and control functions for the mission. The PGNS uses inertial components for guidance, an optical device and radar for navigation, and a digital computer for data processing and generation of flight control signals. Okay, so right below is the figure 2.2-1, which is the guidance, navigation, and control subsystem. It seems fairly complicated. A lot is going on in there. It has some sort of display and keyboard assembly. Data entry. Trying to figure it out as I'm reading it, actually. Landing radar. Is that really the primary? Is that? I guess that's the guidance, navigation, and control subsystem. I guess. Alright. Let's continue. The inertial guidance portion of the PGNS establishes an inertial reference that is used in the central coordination system from which all measurements and computations are made. The inertial guidance portion senses instantaneous velocity and I want to say this as altitude, but it looks like attitude. I'm going to go with altitude. And provides incremental velocity and... Is it attitude? Can I zoom in? I can, in fact, zoom in. How much can I zoom in? It says attitude, actually. I wonder what that means in science terms. Alright, so the inertial guidance portion senses instantaneous velocity and attitude and provides incremental velocity and attitude data to the digital computer for generation of attitude and translation changes. For navigation, the PGNS uses star sightings taken with a telescope and radar for position and velocity calculations. The digital computer establishes an inertial reference using the star sightings. The position and velocity calculations enable the LM-CSM rendezvous and during lunar landing missions enable a safe landing on the lunar surface. With the aid of the inertial guidance and navigation portions of the PGNS and software capability of the computer, the PGNS controls the flight of the LM. The PGNS generates attitude commands to correct or control vehicle motion. During ascent engine or descent engine burns, the PGNS controls LM attitude, engine firing, descent engine thrust, and direction of the descent engine thrust vector. The abort guidance section, the AGS, is a strapped-down inertial system in which the inertial sensors are rigidly mounted with respect to the vehicle, rather than mounted on a stabilized platform. The AGS provides independent backups for the PGNS. It is used only if the PGNS malfunctions. If the PGNS is functioning properly when a mission must be aborted, the PGNS is used to control the LM. The AGS determines the LM trajectory or trajectory. The AGS determines the LM trajectory or trajectories required for the coelliptic rendezvous sequence to place the LM in a safe parking orbit, and controls LM attitude, navigation, and guidance. Rendezvous from the abort point can be accomplished automatically under AGS control or by the astronauts using data displayed from the AGS. When the AGS is used, the CES functions as an autopilot. The CES uses the AGS input signals and manual control signals to control LM attitude and translation. Rendezvous radar and transporter, the RR, operated in conjunction with the RR transponder in the CSM, is used to acquire and track the CSM before and during rendezvous and docking. When the PGNS is in control, normal operation, the RR provides the PGNS and cabin displays with a line of sight LOS, range and range rate data, and LOS angle and angle rate data with respect to the CSM. During AGS operations, an astronaut furnished these data to the AGS. The RR LOS is defined as the line of sight direction between the CSM target and the RR antenna. The RR also tracks the CSM target during the coasting and engine burn descent phases of the mission to supply tracking data for any required abort maneuver. During the rendezvous phase, RR performance is evaluated by comparing RR range and range rate tracking values with Manned Space Flight Network (MSFN) tracking values. A large deviation from the MSFN tracking values, some of these are tongue twisters, I'm not going to lie to you, indicate a gross error in the RR range and range rate data. Data pertaining to the RR shaft and trunnion axis angles and IMU gimbal angles are also transmitted to the MSFN for comparison with the ground tracking data. The RR transponder, a radar receiving and transmitting target, increases the RR maximum usage range capabilities by reducing the RR transmitting power losses versus range from fourth to second power as compared to skin track radar. By providing the RR with a discrete radar transmitting signal to acquire and track, the transponder makes the CSM appear to the RR as the only object in its field of view. On acquiring the RR signal illuminating the CSM, the transponder sidesteps the RR 3-tone phase modulated carrier frequency down to 40.8 MC to 9792 MC, and then transmits the phase coherent 9792-MC carrier frequency for the acquisition by the RR. The 3-tone modulation of the transponder transmitted signal is kept phase coherent with the RR transmitted signal received by the transponder. Alright, the landing radar, or the LR, provides the PGNS and the astronauts with slant range and velocity data for control of descent to the lunar surface. Based on these data, the PGNS calculates control signals for the LM, rate of descent, hovering at low altitudes, and soft landing at the selected lunar site. The LR is activated at approximately 50,000 feet above the lunar surface and remains activated until touchdown. Slant range data are available to the PGNS at approximately 25,000 feet, velocity data and approximately at 18,000 feet. Oh, that's the end of that. Okay. So here we have figure 2.2-2, which shows the LM rendezvous radar and the CMS target orientation. So this is the lunar module right here, and it's showing all the different access points. I guess it's facing forward because this is the line of sight with the rendezvous radar antenna. And then the transponder is a separate vessel. I see. No, I don't see. I know I just read about this and I should understand, but I don't. So the antenna pointing error angle is just these couple of degrees. The return frequency is 9792 MC. Yeah, we know that. The line of sight goes straight to the transporter. Sure. Alright, let's talk about the control electronics section. The CES controls LM attitude and translation about and along the 3LM orthogonal axis by processing and routing command signals to fire any combination of the 16 thrust chamber assemblies, the TCAs, of the reaction control subsystem, RCS. The attitude and translation control signals originate automatically from the PGNS or the AGS, or are provided by an astronaut. The CES also processes on and off commands for the ascent engine and the descent engine to provide major LM translations. The direction of the descent engine thrust vector is also controlled by CES. Orbital rate display, Earth and Lunar. The Ordeal provides an alternative to the attitude display and pitch only. When selected, the Ordeal produces an FDAI display of computed local vertical attitude during circular orbits around the Earth. Subsystem interface, GNNCS, MPS interfaces. The GNNCS provides a sequence of commands to the main propulsion subsystem, the MPS, to control the ascent and descent engines. For ignition to occur, the engine must first be armed. Normally, this involves setting an ENG ARM switch, panel 1, to the desired position. Depending on the switch setting, a discrete is generated in the CES to enable the start push button, panel 5, for an ascent engine operation, or to operate actuator oscillation valves for this. Sorry guys, I'm getting really give me 1 second. Okay, the GNNCS provides a sequence of commands to the main propulsion system, MPS, to control the ascent and descent engines. For ignition to occur, the engine first must be armed. Normally, this involves setting the ENG ARM switch or panel 1 to the desired position. Depending on the switch setting, a discrete is generated in the CES to enable the start push button, panel 5, for ascent engine operation or to operate actuator isolation valves for the descent engine operation. Under abort or emergency conditions, the abort and abort stage PBs are used to perform the arming function. When the PGNS is in control, on and off commands are generated automatically by the LM guidance computer, the LGC, under program control, or manually with the start, panel 5, and stop push buttons, panel 5 and 6. With the AGS in control, on and off commands are generated automatically by an abort guidance computer, the Abort Electronics Assembly, AEA, under specific routines, or manually with the start and stop push buttons. The on and off commands actuate pilot valves which hydraulically open and close the fuel oxidizer shutoff valves. Under emergency conditions, the ascent engine ignition sequence may also be automatically completed through the use of the abort stage push button, panel 1. If the ascent engine on command from either computer is lost, a memory circuit in the CES keeps issuing the commands to ascent engine. The descent engine receives on and off commands, throttle commands, and trim commands from descent engine control assembly, DECA. The ignition sequence commands for the descent engine are generated automatically or manually in a manner similar to that of the ascent engine. On and off commands are routed from either computer, dependent on the guidance mode selected, or start and push buttons through the DECA or the DECA, however you want me to say it, to actuate the descent engine pilot valves. Throttle commands to the descent engine are generated automatically by the LGC under the program control, or manually with the thrust/translation control assembly, TTCA. The TTCA can be used to override the LGC throttle commands. The AGS cannot throttle the descent engine. Throttle commands cause the throttle actuator of the descent engine to change the position of the flow control valves and vary the injector orifices of the engine. Changing the position of the flow control valves changes the quantity of the fuel and oxidizer metered into the engine and thus changes the magnitude of the engine thrust. The GNNCS generates trim commands to tilt the descent engine to control the direction of the thrust vector. The descent engine is tilted about the LM y-axis and z-axis to compensate for the offset of the center of gravity due to the fuel depletion during descent engine operation. The thrust vector is controlled by the LGC with the aid of the two gimbal drive actuators, GDAs. The GDAs are pinned to the descent engine and the LM structure along the y-axis roll and the z-axis pitch. When actuated, the GDS extend or retract a screw jack actuated arm that tilts the engine to attain and desired thrust vector. Thrust vectors control the ascent engine is achieved through firing a selected upward firing TCAs. GNNCS RCS interface. The GNNCS provides on and off commands to the 16 TCAs, referred to the thrusters or jets, to control the LM attitude and translation. In the primary mode of operations, PGNS in control, the LGC generates the required commands and sends them to the proper jet drivers in the CES. The jet drivers send selected on and off commands to the RCS primary solenoids. In the secondary mode of operation, AGS and control, the AGA supplies the CES with attitude errors. The Attitude and Translation Control Assembly, ATCA, in the CES uses these inputs to select the proper thrusters for the attitude and translation control. The thrusters are controlled manually with the Attitude Controller Assembly, the ACA, and the TTCA, the The ACA provides attitude commands, and the TTCA provides translation commands to the LGC during the primary mode of operation and to the ATCA during the secondary mode of operation. The ACA can fire the thrusters directly during the pulse, direct, and hard over modes, bypassing the LGC and AEA in the ATCA. The 4 downwards firing thrusters may be fired by pressing the positive X transol button, panel 5. The on and off commands supplied to the thruster take the form of a step function. The duration of the signal determines the firing time of the selected thrusters, which ranges from the pulse which ranges from the pulse less than 1 second to steady state 1 second or longer. Each thruster contains an oxidizer solenoid valve and a fuel solenoid valve, which, when open, pass propellant through an injector into the combustion chamber, where ignition occurs. Each valve contains a primary automatic solenoid and a secondary direct solenoid, which opens the valve when energized. On and off commands from the ATCA are applied to the primary solenoids. The direct commands are applied to the secondary solenoids. The GNNCS EPS interface. The Electrical Power Subsystem, EPS, supplies primary DC and AC power to the GNNCS. This power originates from a 6 silver Zine battery, 4 in the descent stage and 2 in the ascent stage. The descent batteries feed power to the buses during all operations, before staging. Immediately before staging occurs, ascent battery power is switched on and descent battery power is terminated. A dead face relay circuit dead faces the descent batteries when normal staging occurs. Under emergency conditions, when the abort stage push button is pressed, a power switchover command which... Oh Lord, am I skipping a page? Which, they left me on suspense here. At least scan 8, right, guys? I don't even know what's going on right now. Rendezvous radar and transporter located in the CSM. Okay. Hold on, where's the start of this? This is just the rant. So it goes to, okay. Let's go to the primary guidance and navigation section here. So a lot of things are coming in. We got the landing radar with the altitude, velocity data, altitude rate. So here it says altitude, but you know I zoomed in and it says attitude. I'm not even lying to you right now. I'm not gonna be gaslit by this manual. There's an explosive devices subsystem, which is the ascent tank, pressurization and staging to the supercritical helium. Reaction control subsystem. What is happening? I wish I could see how this is connected better, because I don't even see. This should say generator or commands. I guess it's this. Oh shit, I clicked on it. It should have been up a little higher, but then what the crap is that all about? No, that doesn't make any sense. I think this goes all the way up here. I don't even know. Moving on, gang. Which initiates dead facing automatically is routed to the EPS. The 28-volt DC battery power is routed through an inverter to provide 115-volt, 400 CPS AC to the GNNCS equipment. Please refer to the paragraph 2.2.3.8 for a functional description of the power distribution. Wow. 2.2.3.8. We got some time, there's some ways to go before going to the 2.2.3.8, but we'll get there. Okay, we're going into the ECS interface, which is the environmental control subsystem. It provides the thermal stability for the temperature-sensitive electronic equipment of the GNNCS. The electronic equipment, except the inertial measurements unit, or the IMU, is mounted on the cold plates and rails through which the ECS coolant ethylene glycol water solution is routed to remove heat. To cool the IMU, the coolant flows through its case. Refer to the paragraph 2.2.4.12. The heat that is removed from the equipment is vented overboard by the ECS sublimators. The CS interface, the communication subsystem. So the communication subsystem CS interface directly with the GNNCS when the astronaut uses the push to talk switch on the ACA. When the switch is pressed, the ACA issues a DC signal that enables an audio center in the signal processing assembly of the VHF/AM communications. I know I said communications, but it's communications, and I'm hoping you're sleeping by now. This enabling signal allows the audio signals from the microphone to be processed by the CS. Automatic never fails. Automatic remote control of the LGC is provided through the use of a digital uplink assembly, DUA. Uplink commands from the MSFN processed by the DUA are used for program control. The CS interfaces indirectly with the GNNCS using the VHF/AM communications for voice uplink commands. It also interfaces with a tone generator in the CES. The generator, enabled by command from the master alarm circuit of the instrumentation subsystem, or the IS, issues a 1 kC tone to the astronaut's headset as an indication of subsystem malfunction. Good to know. The EDS interface. The GNNCS interfaces with Explosive Devices Subsystem. Oh, see? I was curious about that. Or the EDS. By supplying a descent engine on signal to the supercritical helium explosive valve and an ascent engine on switch. And an ascent engine on signal, which initiates the staging sequence. When the descent engine is operated for the first time, the master arm switch is set to on, so the supercritical helium explosive valve is blown when the descent engine on signal is issued. All other normal pressurization and staging sequences are initialized by the astronauts. During the emergency situations, the abort stage push button, when pushed, shuts down the descent engine and pressurizes the APS, blowing the helium tank explosive valves that are selected by the ASC HESEL switch panel number 8. It's a lot of letters today, guys. After a time delay, the GNNCS generates an ascent engine on signal, which state signal is routed from the EDS dead phase switch to the ATCA and to the LGC. The signal automatically selects the power deadband for the RCS control during ascent engine operations. Let's talk about the IS interface. The instrumentation subsystem, the IS, senses GNNCS physical status data, monitors the condition. Let me start over. The instrumentation subsystem IS senses GNNCS physical status data, monitors the GNNCS equipment, and performs the in-flight checkout. The data signals are conditioned by the Signal Conditioning Electronics Assembly, or the SCEA, and supplied to the Pulse Code Modulation and Timing Electronics Assembly, the PCMTEA, and the Caution and Warning Electronics Assembly, the CWEA. The PCMTEA, or the PCMT, changes the input signals to the serial digital form for transmission to the MSFN. I think that's my least favorite abbreviation. I always get tongue twisted. The MSFN. The CWEA checks the status of the GNNCS by continuously monitoring the information supplied by the SCEA. When an out of limits condition is detected by the CWEA energizes one or more of the caution and warning lights associated with the GNNCS. The LGC interfaces directly with the IS supply a 1.024 MC primary timing signal for the PCMTEA. The timing signal is used in generating timing and sync signals required by the other subsystems. The IS supplies the LGC with telemetry data, start and stop commands, and sync pulses for clocking out telemetry data. It also supplies the AEA with telemetry stop commands and sync pulses. The functional description: that GNNCS comprises two functional loops, each of which are independent guidance and control paths. The primary guidance path performs all functions necessary to complete LM mission. If failure to the PGNS occurs, the abort guidance paths can perform all functions necessary to effect a safe rendezvous with orbiting CSM. The primary guidance path comprises PGNS, CES, LR, RR, and selected propulsion sections. See Figure 2.2-4. The CES routes the guidance and navigation data from the PGNS and applies them to the descent or ascent engine and in selected TCAs. As inertial measurement units, IMU, which continuously measures attitude and acceleration. I'm just going to say altitude because I feel stupid saying attitude, but it looks like a T. Which continuously measures altitude and acceleration, is the primary inertial sensing device of the LM. The LR senses LM slant range and velocity. The RR coherently tracks the CSM to derive LOS range rate, and angle rate. The LGC is the central data processing device to the LM. The LGC uses star sighting data to align to the IMU, using inputs from the LR, the IMU, the RR, the TTCA, and the ACA, and the LGC solves guidance, navigation, steering, and stabilization equipments. The stabilization equations necessary to initiate on and off commands for the descent and ascent engines, throttle commands, and trim commands for the descent engine, and on and off commands for the thrusters. God, that was a mouthful. I can't believe I did that better than most of what I've read today. This is difficult, guys. Don't knock it till you try it. My God. Alright, I'm gonna wrap up this page. Control of the LM when using the primary guidance path ranges from fully automatic to manual. The primary guidance path operates in the automatic mode or in the altitude hold mode. In the automatic mode, all navigations, guidance, stabilization, and control functions are controlled by the LGC. It says attitude though. Like, guys, I'm gonna zoom in. Like, you're gonna tell me this is not attitude? Okay, I'm going back. I'm gaslighting myself at this point. This is attitude. I make sense for it to say altitude, but it's definitely attitude. Okay. When the attitude hold mode is selected, the astronaut uses the ACA to bring the LM to the desired attitude. When the ACA is moved out of the detect position, proportional attitude, rate, or minimum impulse commands are routed to the LGC. The LGC then calculates steering information and generates thruster commands that corresponds to the mode of operation selected via the display and keyboard assembly, the DSKY. These commands are applied to the primary preamplifiers in the ATCA, which routes the commands to the proper thrusters. When the astronaut releases the ACA, the LGC generates commands to hold this attitude. If the astronaut commands for jet direct operation of the ACA by going to the hard over position, the ACA applies the command directly to the secondary solenoids of the corresponding thrusters. In the automatic mode, the LGC generates descent engine throttling commands, which are routed to the descent engine via the DECA. The astronauts can manually control descent engine throttling with the TTCA. The DECA runs to the TTCA throttle commands with the LGC throttle commands, and applies the resultant signal to the descent engine. The DECA also applies trim commands generated by the LGC to the GDAs to provide trim control to the descent engine. The LGC supplies on and off commands for the ascent and descent engines to the S and C control assemblies. The S and C control assemblies route the ascent engine on and off commands directly to the ascent engines, and the descent engine on and off commands to the descent engine via the DECA. In the automatic mode, the LGC generates plus x-axis translation commands to provide ullage. In the manual mode, manual translation commands are generated by the astronaut using the TTCA. These commands are routed through the LGC to the ATCA and onto the proper thruster. Lord Jesus Christ. The abort guidance path comprises the AGS, CES, and the selected propulsion section. See figure 2.2-5. And the AGS is a backup for the PGNS. The term abort guidance path is somewhat misleading in that way. Abort situation is normally under PGNS control. The AGS is used only if the PGNS malfunctions. The AGS performs all inertial navigation and guidance functions necessary to effect a safe orbit or rendezvous with the CSM. The stabilization and control functions are performed by analog computation techniques in the CES. The AGS uses a strap-down inertial sensor rather than a stabilized gimbaled sensor used in the IMU. The abort sensor assembly, the ASA, is a strap-down inertial sensor package that measures attitude and acceleration with respect to the LM body axis. The ASA sensed attitude is supplied to the AEA, which is a high-speed general-purpose digital computer that performs the basic strap-down system computations and the abort guidance and navigation steering control calculations. The data entry and display assembly, the DEDA, is a general-purpose input-output device through which the astronauts manually enter the data into the AEA and commands various data readouts. The SES functions as an autopilot when the abort guidance path is selected. It inputs from the AGS and from the astronauts to provide the following: on, off, and TTCA throttling commands for the descent engine, gimbal commands for the GDEAs to control descent engine trim, on and off commands for the ascent engine sequencer logic to ensure proper arming and staging before engine startup and shutdown, on and off commands for the thrusters for translation and stabilization and for various maneuvers, jet selected logic to select the proper thrusters for the various maneuvers and modes of LM control, ranging from fully automatic to manual. Lord. Let's see what we got left here. Quite a bit. Yep. Wow, we're getting into the nitty-gritty. There's a lot of graphs here that I might have to read over. This page is intentionally left blank. It looks like section 2 might be a little deep. Lord, what is this? Oh, we're gonna have a good time. That's what it means. Section 2 is huge, guys. Section 2 is ginormous. This section 2 is so I'm not gonna read this. I'm not gonna read the program numbers. I'm not gonna do that. You guys are crazy. Leave a comment down below if you want me. Am I still in section 2? I sure am. Section 2 is ridiculous. I have gone through so many pages right now. Can you guys believe this manual is almost 1,000 pages long? Lord, over here talking shit. Okay, well, let's at least finish this page, yeah? I'm gonna finish here. Alright, crew, that's all for tonight's readings. You made it through a section of the manual and hopefully into a peaceful orbit of dreams. Sleep well, and I'll see you on the next mission. And if you need me or just need more time, just click on that next video. Bye!